doing on my own. This was studied by Winnie Lee in 92. She studied these difference graphs, and she studied the properties, the graph theoretic properties, such as connectivity, diameter, and girth. Okay, so how does one show that a k-regular graph is connected? Just purely with theory. You know, these finite fields can be very large, and it is certainly not useful to say, okay, draw the graph and see if it's connected. So one way to do it is looking at the trivial eigenvalue k and looking at the multiplicity. So the number of components in the graph is actually the same as the multiplicity of that trivial eigenvalue. Okay, and so here to show that something has multiplicity 1, saying that okay, there's just one eigenvalue that is equal to k, you can do it by saying look at every other eigenvalue and show that in absolute value it's strictly less than k. Okay, so that's what she did. And for that, she used Deline's bound on these Kloosterman sums to show that such a strict inequality holds. Okay, so in her case, it was connected. Okay, so what I've been looking at is the following question. What happens if we replace a finite field by a product, so an algebra instead? Okay, so this is no longer a field, of course, but it's an algebra. But it is, again, you can look at degree n extensions of FQ in the following way, that you look at products such that the sum of the individual extensions, individual degrees add up to n. Okay, so for FQ squared, you have FQ times FQ. That's another one. For FQ cube, you could have FQ squared cross FQ or FQ, FQ, FQ. Okay, so I'm sure you see where I'm going with this. For every partition of n, you can have an étale algebra. So these are called, it's just a fancy word for the same thing. That's a product of finite fields. Okay, so my idea is, what if Winnie Lee's work was just the tip of the iceberg? Okay, so she considered FQ to the 6, but then this is not the only thing that lies, only algebra that lies above FQ. You have all of these, okay? And so it would be interesting to see whether the properties that she studied, how do they vary as you change the partitions? Okay, does, for example, connectivity, does that still carry forward? If you have a triangle in this graph, like, can you find triangles everywhere, and so on? Okay, so that was my motivation to study this problem. Okay, but for that we need to again now set up, okay, these are finite groups. You can view these as finite groups, but then you need now a notion of norm and trace that we had before, and that's not hard. Okay, so you just get the norm by multiplying the individual norms. So here, of course, this means I'm looking at the norm in over FQ. So the FQ to the M1 over FQ for this one, and so on. Here I'm looking at this other extension. So these norms, although I've written n everywhere, it actually means different formulae if you write it down, because the extensions are different. Okay, but we'll just assume that all that is understood and we know what we're doing. So we'll just leave it as n everywhere. Okay. Okay, so similarly for trace, you just take trace of x1, trace of x2. Okay, so this most likely is not just, even though trace is additive, okay, because the individual traces are different. We're talking about trace over different fields. Okay, so unless you're looking at FQ cross FQ everywhere, in that case, yes, you can just add them up, but not otherwise. Okay, so now suppose I wanted to stick to the same set. You look at the norm 1 elements. How many elements are of norm 1? Okay, so here it's easy to see because we already know that how many elements are of norm 1 in any given extension. So if I have x1 to xd, any of the d minus 1 elements, so these can be anything I want, and then this has to be something whose norm is the inverse of the remaining. And so this is why I get, so these can be any unit from I to d minus 1. So q to the mi minus 1, I going from 1 to d minus 1. And then this one has to be something that's in the whose norm is the inverse. And the size of the fiber is actually the same. So it's not just that you have, q, sorry, this should have been down here. Okay. No, these are the number of units. Okay, this is not up here. This is the size of the norm 1 elements, but it's actually the same as the size of any norm. As long as you fix a norm, it has these many elements of that norm. Okay, so these put together give you this size of norm 1 elements. Okay, so now we know the degree of this graph. That's great. Let's look at some pictures. Okay, let's, in small cases, we can draw the pictures. I use Sage to tell me what these graphs look like. So for example, F9 over F3, the graph looks like this. Okay, so there are 9 vertices, and it is an even extension. So this is an even extension, which means you can see there are arrows going both ways, and you can identify the vertices and get the undirected graph. Okay, so unfortunately, Sage won't just take the same graph and merge the arrows. I would have liked that, but I couldn't figure out how to do it. But you can ask for it to, give the undirected version, and then it printed this. Okay. Now let's see some odd degree graphs, but I've removed the arrows so that you can actually see the edges. Otherwise, the arrows were very fat, and I couldn't figure out how to reduce that either. But anyway, the idea is, very, very quickly, see for something so small, F3 squared cross F3 and F3 cube, which is really nothing. Q can be, a 6-digit prime power, and so then it's an absolute jungle. But it's already, bit of a jungle here itself. Okay, so but it's nice to see pictures. Another thing I don't get to do much in my number theory talks, so I took the opportunity to show. Okay, so here, so these are both degree 3 extensions, and you can see these are different graphs. Okay, so this is an algebra of degree 3, F3 squared. So this is corresponding to the partition 2, 1, and this is corresponding to just the partition 3 of 3, and the graphs are clearly different. Okay, and because we've already calculated the degree, you know that the degree of these two graphs are different. But something is interesting when you look at the spectrum. Okay, now when Delin showed that you have these Kloosterman sums being similar, etc., he did it for Étale algebras in general, not just for finite fields. Okay, so you can talk about Kloosterman sums for Étale algebras, and it looks the same. It's just that instead of K being a finite field, it could be a product, and it's exactly the same quantity that we saw before. Okay, so except for finitely many of, so now for each value in K, you should get an eigenvalue. And except for finitely many, and those finite exceptions are where, one of the AIs are 0, then you can explicitly say what the eigenvalue is. And otherwise, it's this thing. I mean, you can explicitly say in the sense you don't have any characters floating around. It's an actual number that you can write down, but here you're using characters. And this is also a generalized Kloosterman sum. So we know the distribution here too. Okay, so it's interesting that, there's a huge overlap. So except for finite, a small set, there is an overlap in the eigenvalues between FQ to the n and a product whose degrees add up to n. But these are clearly not isomorphic graphs because the degree is different. Okay. And the distribution in the case of the quadratic extensions. Okay, so when you look at FQ squared over FQ, or FQ cross FQ over FQ, these are both, I can view them as quadratic extensions. It's given by what is known as the Sato-Tate measure. Okay, so this is what basically drew me to this whole area, because in my other research works, I study sequences distributed using the Sato-Tate measure, but they come from modular forms and elliptic curves. And here there was something sitting in graph theory coming from groups, of course, but also having the Sato-Tate measure. So that's where I got drawn into this. Okay, so this is about the spectrum. What about connectivity? Unlike the case of Vinili's graphs, here not every Étale algebra graph is connected. For example, F3 cross F3 is a union of 3 triangles. In fact, F4 cross F4 is a union of 4 K4s. Okay, and F2 cross F2 is 2 line segments. Okay, so it looks like, oh, maybe, you know, FQ cross FQ is a product of complete graphs, that many complete graphs, but no, that this kind of pattern stops with this, and everything else after that, except for F2 cross F2, because here there's only one element of norm 1, right? The element 1, 1, 1, 1 is the only thing. There's no other choice. Otherwise, you'll have 0 somewhere, and then that element is not, we are not considering that at all. Okay, it has norm 0. Does it have norm 0? No, we won't consider them. Okay, so we're only considering in F2 cross, and then F2 cross is just the single element 1. Okay, so these are easily seen to be disconnected because these are just union of line segments. But F3 cross F3, F cross or F4, we've drawn it. We can see that they're disconnected. And it turns out that everything else is connected. Okay, and we do the same thing. You see that a bulk of the cases can be treated using what Vinili did. You look at the bound for the Kloosterman sums and show that every eigenvalue that's not the trivial eigenvalue is strictly less than this bound. I mean, strictly less than the degree of the graph. But this only works for a bulk of them. Sometimes the Deline's bound is not enough, and the ones that we can't use are this set. And the way to go about is, okay, for these 3 you can draw it, but the remaining cases you just use linear algebra. Okay, so what does it mean to say 2 vertices are connected in our case, right? So if you can find a path, so in some sense I'm doing more, I'm trying to find, show that it's path connected. Okay, so if I start from G, everything is something like that, right? S1 plus S2, say plus S3, right? So what I'm saying is, so I look at an arbitrary point in my graph and ask, can I write this point as a sum of SIs, right? And if I can do that, then I'm done. So in some sense, I start from the identity element and then add, it's something like I'm connecting it all the way to the identity. So since FQ is a field, I look for a basis consisting of norm 1 elements, because now I'm only allowed to add using norm 1 elements, and then I'll be done. Okay, so that's what I end up showing, that you can actually find a basis consisting of norm 1 elements in the remaining cases. Okay, so it's so nothing deep going on, but it's it's fun to show. Okay, so connectivity was fine. Girth is the length of the shortest directed cycle in the graph. Okay, and girth is something what people are interested in, because say, for example, if you want to apply this thing to networks, girth will a large girth is sort of more preferred. So you want to see, okay, how many, how if you have a cycle, then you know that if something breaks in that cycle, that entire you better have enough interconnections so that the other things in the cycle are not affected. Okay, so anyway, so there is I think there's a talk tomorrow about expander graphs, and maybe that will be explained there about these things of girth, how girth is important in networks. But for me, I'm just looking at it as at a theoretical perspective. And here it's just like I want to add the norm one elements. What is the smallest t I need to add so that they add up to 0, right? So if I have some g, I want to know what is the smallest, sorry, okay, I don't know what that, and then it goes to, okay, and then I come back. So this will be plus S1, this will be plus S2, and this will be plus S3. So if I come back to this, that will mean I have done G plus S1 plus S2 plus S3 is equal to G. And so it's nothing but S1 plus S2 plus S3 is 0. Okay. And so if I solve such an equation, I get a three cycle. Okay. So if T is the smallest that I can get, then the girth of the graph is 3. Okay, now because we are identifying multiple edges between two vertices, so if I have something like that, as we've seen in some examples, I won't say that the smallest possible girth is 2, because I will identify these and just make it as one edge. Okay, so when I do that, I'm really just doing it this way. And when we have an undirected graph, then there is this directed thing doesn't really play a role, but it plays a role in actual directed graphs. Okay, so here it doesn't matter which direction I am. I know that behind all this, I know I can actually go in both ways. Okay, so it's fine. Okay. Okay, so what did Vinili show? In her case, it was rather simple in the sense that there were essentially two cases, either 3 or 4, and it had girth 4 in this one specific case of fq squared, with q being 1 mod 3. Okay, every other fq to the n over fq, the girth was 3, except in this case, and here the girth is equal to 4. But the general case involves solving a system of linear equations over finite fields, which when I started, looking into this, I realized, we do so much of linear algebra teaching in colleges. In solving linear equations, it's so fundamental, but you change your R or any algebraically closed field to this finite field, and things become very tricky very soon. Okay, so you don't have such a nice because there's this whole collapse of when you add, multiply, you're not going too far. And so in some sense it seems like how the arithmetic is, it sort of makes the solving of linear systems difficult. So if you look up any kind of result on linear systems over finite fields, it will have some conditions on your system. Then you get something. So some small thing, you need this, and then you can solve this linear system, or maybe there's a bound on the number of solutions and so on. But you don't have something as clear cut as solving linear systems where your base field is R. Okay. So now, okay, I have this problem. Still not too bad. Okay, because I have Vinili's results, and the idea is that, okay, first see how much we can just get through with just looking at what she did. So if I have fq to the m1 cross fq to the m2, I know over here, so everything here now is of the form, say a1, a2. I want to see b1, b2 plus c1, c2 to be 0. Okay, so I want to see if I can solve something like this, where this is of norm 1, this is of norm 1, this is of norm 1. But if each of them were individually of norm 1, then of course the product will have norm 1 by, we know that n norm of x1, x2 is just norm of x1 times norm of x2. It's not true that they individually have to have norm 1. Okay. If they have norm 1, the product is norm 1, but this could be something like 3 and 3 inverse, and these things will also have, so such a number will also have norm 1. Such an element will also have norm 1. Okay, so but we can say if they in fact had each of them having individual norms to be 1, then I'm done, because now I can take, this triangle sitting here, this triangle sitting here, put them together, and I get a triangle in the product field. Okay, so that's clearly we should, throw away all these cases, because we can we don't have to do any extra work to find these triangles. Okay, but where was the difference? The difference was that when she had FQ squared over FQ, where Q was 1 mod 3, then she had girth 4. And when I add elements to the graph, vertices to the graph and edges to the graph, the girth can at most reduce, right? Sorry. Yeah, girth can at most reduce. It won't go up. But here the minimum girth is anyway 3. So from 4, it can at most jump down to 3, or it stays 4 as it is. Okay, also, she didn't have, something like FQ. She always looked at extension. So you didn't look at FQ or FQ. So here we have these cases to take care of. So FQ to the M cross FQ and FQ to the M cross FQ squared. Okay, and I mean, in this case, it's only when Q is 1 mod 3. If it's 2 mod 3, we know how to deal with it. Okay, so, but this is still an infinite family. Okay, we've reduced, the general FQ to the, I've written it here. So we've reduced this entire setup to this, but this is still an infinite family. Okay, and let's work out one simple case, okay, to see what's going on when I say system of linear equations and so on. Okay, so here, what are the elements of norm 1? It's easy to write. It's just A and A comma A inverse. Okay, because I know that the norm is multiplicative, and so B has to be A inverse. Now, if there's a triangle, I'm trying to solve something like this, right? Because these are all the x coordinates here. So these are the sort of first coordinates, and these are all the second coordinates. Okay, so z inverse, x inverse, y inverse. Now, without loss of generality, we can take z to be 1. Okay, we can just normalize it. It won't change anything. And also understand that 1 plus x plus y is 0 will mean that we want y to be minus of 1 plus x. Okay, so we're down to, and then we substitute this in the second equation to get 1 plus x inverse minus 1 plus x inverse to be 0. Okay, and so now we've boiled it down to one equation, although you have inverses, so it's not as straightforward. But you simplify it to get x squared plus x plus 1 is 0. Okay, and this should be familiar to you, because this is the equation you solve to get primitive cube roots of unity. So now, okay, we know that they exist in C, and but we are working in FQ cross. So now we ask, when does a finite field have a primitive cube root of unity? Okay, so starters, it should be an element of order 3. Okay, and we are in a finite group, so it should divide the order of the group. So 3 should divide. So we are looking at this as our group. So 3 should divide Q minus 1. So Q should be 1 mod 3. Conversely, if you start with, if you know that your field has a cube root of unity, 1 plus omega squared is 0. Also 1 plus omega inverse squared is 0. Okay, and so this satisfies what we wanted. 1 plus x plus y is 0, and 1 plus x inverse plus y inverse to be 0. Okay, this was the equation set we wanted to solve, and here we have the solution. Okay, so this means that the graph of FQ cross FQ has girth 3 if and only if Q is 1 mod 3. Okay, so, and in these cases, even in Vinili's case, so once you know that it's not of girth 3, showing that it's girth 4 is pretty easy. But showing that it is actually girth 3 and it can't be, girth 4, okay, you found a quadrilateral, but the fact that you can actually still find a triangle is usually the hard part. Okay, but then things start to get complicated once we solve equations over extensions. Okay, maybe okay, maybe I'll skip this. Okay, for example, in this case, we finally get a quadratic equation which happens to be reducible. Okay, but then for if something is in the base field, the norm in the quadratic extension is just the square, and again you get something. So finally, it's like you're working with primitive cube roots of unity. Every time you have something like that, then it's fine. Otherwise, you have to. It's likely that your um, algebra does not have a triangle, or you have to work harder to find a triangle. So let me just summarize what we're able to see. That for FQ cross FQ and FQ squared cross FQ, sorry, this thing should be here. It has girth 3 if and only if Q is 1 mod 3. Okay, and the remaining cases of product of two fields, you can use Vinili's results, or I mean, it's just a little step above what she did. Okay, but that is not too far away from the tip of my iceberg. My iceberg had like a whole triangle here. Okay, this is length 1. I just did a length 2 partition, and we have all this to cover. Okay, but length 3 and length 4 also similar strategy works. There are, you isolate the cases that you cannot do without with Vinili's work, and here they all need different proofs, but they end up having girth 3. And using the length, triangles in length 1, 2, and 3 partitions, you can go to 4. Okay, so we are able to see that if as long as D is 3, 4, and 2 case was already considered. But in the length 3 and 4, everything has girth 3. There are no exceptions. Okay, so things starting to look more uniform now. Okay, but then we can't keep doing this forever. 4, 5, 6, go on. So we appeal to something in number theory. Okay, so it is elementary number theory problem. You take two coprime integers a and b. So this is like, if you want to divide your class into groups of size a and b, what is the biggest number such that you cannot do it? Okay, so eventually you will always be able to do it, and that requires some thought, but not too difficult to see. So you want the stage after which everything bigger than that can be divided into groups of a and b. And the solution to the Frobenius number problem says that the biggest number that cannot be written as MA plus NB is this term. Okay, so using the fact that, if I have now FQ to the M1 cross on to the FQ to the M3. So if I have triangles individually, I can group them up. So I know that. Similarly, I can group 2 at a time, 3 at a time, have M here, M4 product and an M4 product, and individually calculate the triangles and so on. So I want to know what is the biggest length. I cannot do this, and it gives me 5. Okay, and it turns out that in fact there is an exception. So initially I thought, okay, up till 3, 4, everything seems to have a triangle, so maybe that's it. I don't have to do anything more. And now using Frobenius number problem, I know that as long as the length is 6 or more, I'm done. Okay, so they all have triangles. But in F5, the specific product of 4 product of F5 seems to, this has girth 4. So somehow there's some, the fact that there are odd number, you have only 5 elements and there are 5 copies. The simultaneous equation is you cannot solve it. It's easy to show that you cannot solve this particular equation, but I'm stuck at a point where I want to show that no other exceptions exist. Okay, so this is a conjecture that partitions of length 5 all have girth 3 except this one. So this is the only problem case. And oh yeah, so all this was for not characteristic 2, but it's not hard to deal with characteristic 2. It's mostly 3 except if one of the MIs are 4. MIs are 1, then the girth is 4. So the final result, so in progress because of this case here, is that you have girth 3 except in these cases. Okay, and this thing remains to be solved. Okay, so in progress. Okay, it's very annoying. Just one thing missing, and stopping me from finishing this. But yeah, it's that's how research is. Anyway, so that's it. Thank you for your attention.
So thank you, ma'am.
Yeah.
Thank you for the talk. Also, is there any questions from the audience?
Like in all the algebra extensions that you consider, like for some q power n, like all the partitions. So is there any unifying, like is there any invariant among the graphs, like throughout, like if, for each, no matter what partition you consider?
You mean something that's, I mean, the girth and these things are also invariants?
Right.
No, I didn't understand. You're asking if there is something that's common, that some property holds.
Yeah. For each partition, like no matter what extension you consider.
I mean, I've only studied connectivity and girth, and they haven't shown uniformity. I don't. So it seems like, eventually it gets uniform. So even though it's disconnected in very small cases. Similarly, for 4, it's very isolated. But for most part, it seems to be fine. It seems to be following the same pattern. But I've only studied these two, and you can suggest some property to check, and I can try to work on that. But girth and connectivity is the only thing I've looked at.
Also, is there like have you tried thinking about like other generating sets? Like, is there any are there any nice properties in that case?
No, so this was useful because you know exactly what the spectrum is, and so it's like an interesting graph to consider, right? It's like, so otherwise you have to see what you have this formula that you have the eigenvalues are, S belong to S, psi of S. Okay, so this thing should make sense. If this is an interesting quantity, like in this case, it was actually something that's interesting to number theorists. Then you want to know more about the graph because there's some action happening. But this is a priori just looks like, okay, you can write it, but it might not mean anything, right? So for me, the motivation was coming from here. But sure, we could, you could choose another set. So norm 1 doesn't change much if you change the norm, I think. Like if you take any fixed norm, you're likely to get similar behavior. But if you're asking for something which is not related to norms, I don't know if anything has been done. Like with respect to this is what you're saying, no? Like choose a different S.
Right, yeah.
Yeah, no, I'm not aware of other work done in this area.
Okay.
Yeah, thanks for these questions.
So yeah, now I would like to thank ma'am for giving this talk. In means we have some technical problems still. Thank you for the cooperation. Thank you, ma'am, and also thank you to the participants to cooperate and attend this talk. And since we have still 3 minutes left, I would like to ask for a group photograph with ma'am, and I would like to ask everyone to open their video cameras if possible.
No, just a minute. I put some things in the chat.
Oh.
Do you have any block matrices coming from your graph of the thing? Because G plus S, G plus 2S, G plus TS, that completes a cycle. So you can.
So no, the block matrices will come if you have different components of your graph.
Yes,
like
yes, right. So that might help you to study the spectral theory. You see, that is what my idea is. Okay. So like the G with G plus S, G plus TS, then G with G plus S dash not any multiple of S. You know, so
Okay.
maybe you can make some block matrices, and there is a lot of theory developed for block matrices.
Okay.
Okay,
Thank you.
that is one thing. And you know, moreover, these finite fields, you know, they give rise to unitary bases, unitary
Okay.
systems, and algebras also give unitary systems. Now, for coming from fields, the commuting systems give us mutually unbiased bases in quantum information theory, and
Okay.
fields give us overlapping commutative systems. And from non-overlapping, we can construct rank 1 projection basis coming from the eigenvectors, you know. But for overlapping commuting systems, we cannot do that, so we have to shed some. And how to shed, we have done, 4 of us have done it in a paper in Reviews Mathematical Physics. You see, you said you are doing algebra instead of field. So we also did algebra instead of field, but we did it with respect to unitary bases in the matrix algebra. Unitary bases, their eigenvectors of commuting subsystems will give us rank 1 projection basis. Okay? And they will be mutually unbiased also. And from algebra point of view, we had to take overlapping commuting systems, their rank 1 projections, and then there were some common ones. So we gave a method how to shed the common ones, you know, or reduce the number. And it is in Reviews Mathematical Physics 2021, June 2021.
Can we join again and means, because we have to join again and we'll